Hey everyone, so this is discussion number 6, and I'm going to be talking about Boolean logic and synchronous digital systems. So we'll get started with Boolean logic. So I think the most important thing about Boolean logic is that 1 is what we call true, and 0 is what we call false. And besides this, you've probably seen a lot of this in other classes if you've taken a discrete math class, for example. We do write operations in very interesting ways, I guess. For and, we use a multiplication sign. So we do A, B. This means and. So A and B. And for or, we use a plus. So this does not say A plus B. This is A or B. Okay. And finally, for not, we just put a little bar on top of it for not A. Another operation you'll see sometimes is XOR, which looks like this, but there's no examples of it in this worksheet. Now, if you look at the okay, interesting. If you look at the worksheet, you'll see that we have a lot of rules. We have the commutative property, the associative property, the identity property, the null property, right? And all of these are just different rules that occur for Boolean logic. One that I find really useful and maybe a little bit hard to understand is De Morgan's rule. And De Morgan's rule basically says that not A and B is equal to not A or not B. Okay, which may seem a little bit confusing, but the way I like to think about it is that not A and B is the same as, this, not A and B. And if we distribute out the not, we get not A, right, not and, not B. And the opposite of and is or. So this is not A or not B. Okay. Another logic law that is not on the sheet is the uniting theorem, which I always found very useful for a lot of calculations. Without the uniting theorem, you can still do a lot of these Boolean logic calculations, but they involve a lot of thinking or maybe a lot of excess work, and this can cut it down considerably. So I would write this down for sure. So it's if you have A or not A and B, this is the exact same thing as A or B. And I will give a quick proof by observing. So the thing about the uniting theorem is that if B is true, then this entire expression is true. And the reason is because the only two possibilities are that B is true and A is true, or B is true and A is false. Now, if B is true and A is true, then we know this expression is true because this is true. And if B is true and A is false, then we know this expression is true. So no matter what, as long as B is true, this whole expression will be true, which is why we can say that A or not A and B is equal to A or B. If you want a more formal proof, you'll have to do it yourself, because I don't care. Okay. So let's go over some examples. I'm going to be using expressions from the worksheet. I'm not going to write them all out here, but it might be helpful to have a copy of the worksheet open. Okay. So the first question on the worksheet is 1.1. And 1.1 says simplify this Boolean expression A or B and A or not B and C. So yeah, you can try to work on this on your own and pause the video or something, and then I will do it in a second. Okay, the second is passed. So the very first thing that I would do in this scenario is take a look here and realize that I can sort of distribute out these groups just like if it was in regular arithmetic. So I'm going to FOIL, which is just applying the distributive property on your sheet twice, right? And what I end up with is A and A, right? Or B and A, or A and not B, or B and not B, right? And the whole thing and C, right? So, yeah. Okay. So now I know from the idempotency property, okay, which is the one that says that A and A is A, okay? I know from the idempotency property, so let me write that down, that this whole thing is equal to A or B and A, or A and not B, or B and not B, right? All ANDed C. And now I know from the inverse property, okay, the inverse property says that A and not A is 0. So we know here that B and not B is actually 0. So that whole thing becomes 0. Okay. So now we have A or B and A, or A and not B and C. Okay. And now one thing we can do is we can factor out the A, right? So this is the distributive property backwards, it's factoring. So we'll take out the A and we'll get A and 1 or B or not B, all and C, right? And we'll notice that everything in this parentheses, right, everything here, that is all equal to 1. And the reason for that is the null property, right? The null property says that 1 or a bunch of stuff is just 1. So let me get that written down, null, and this whole thing becomes A and C. Okay, so that's our final answer. Now, if you really want to check that this is the correct answer, what you can do is you can make a truth table. So you can write out every single combination of A, B, and C, right? And then you can do our initial expression here, which is A or B, and A or not B, and C. And you can do our second expression, our simplified one, which was A and C. And you can just sort of compare these. So we'll start off with every combination of A, B, and C. Okay. And, okay, I really don't want to solve this, so we'll just, I have the answers. So if you actually bother doing this, you'll see that this is all zeros except for the first 2 rows. And this one is also all zeros except for the first 2 rows. So we did it. Good job, us. Must be really good at this class. It's like I'm a TA or something. Okay. All right, 1.1b, right? Okay. So 1.1b, we have another expression we want to simplify. So it looks like this: not A and not B and not C, or not A and B and not C, or A and B and not C, or A and not B and not C, or A and B and C. Oh, that's an and. Or A and not B and C. Okay, so this is like every single possible combination. It's actually not, because there's 9, right? Because no, there's 8. 2 times 2 times 2. Okay, yeah, you didn't hear that. There's 8. So the first thing that we want to do here probably is notice that a lot of these terms have similar letters in them. For example, there's lots of C's, right? And especially there's a lot of not C's. So maybe we could do something with that. I could have also alternatively just looked at any of the, notice that there's a lot of B's or a lot of A's, but we'll do the C's just arbitrarily. So this, if we factor out the not C's and the C's, we'll get this, right? Okay, looks good to everyone. And now we're stuck again, right? But we can just do the same thing we did last time and factor out something else, right? So in this case, I'm going to say, okay, well, there's a lot of B's or A's. It doesn't really matter. Maybe we'll do the A's. So there's a lot of A's. So let's just factor those out, okay? And what we got here is now we have not C, not A, and not B or sorry, this is a typo. This should have been not AB because it's from there, right? Okay, so not B or B, and then there's or not C, and we'll take out the A instead of the not A this time, so we get B or not B, and then here we'll get C, A, B, or not B. And now you'll notice that not B or B, right? We talked about this earlier. Not B or B is the inverse property, and so this actually just equals 1, right? So all of these equal 1. And so what we're left with is we're actually just left with this, right? Not C, not A, or not C, A, or C, A. And once again, we can try doing some factoring to simplify this some more, right? So I notice we have 2 A's and we have 2 not C's, so it makes sense to pull one of those out, right? Let's pull out not C. And what we get here is we get not C, not A, or CA, right? And once again, we'll do the same trick here. This is 1, okay? By the null property, inverse property, whatever, it's the same thing. So this will equal not C or C and A. Now this is pretty close to being done, but once again we have the uniting theorem, which comes to save the day again. And we notice that A or not A and B equals A or B looks a lot like what we have down here, which is not C or C and A. And using the uniting theorem, we can come up with that this is equal to A or not C. So that's the end. Yeah, so it's a good thing we had the uniting theorem, because without it, we would have had to do a bunch of annoying computation to get from this step to this step, but I was able to skip it all. Yeah, go me, I guess. If you really want to show that this is equal to that, you can, but I don't want to, so I'm going to skip it. There are always sort of ways to get around using theorems. I mean, a really cheesy thing you can do is you can just, once you get maybe to here, like not C or C and A, right? Once you get here, you can write out the truth table, and it's only 4 long because there's only two variables, right? So it's 2 squared entries. So if we write out the whole truth table here like this, we'll notice that the truth table for this is exactly the same as the truth table for A or not C. So anyway, A or not C has the exact same truth table. So I guess that proves the uniting theorem works, right? It's called proof by one example. Okay, let's move on. Okay, here's 1.1c. So 1.1c says that we start off with this expression, not A and not B and not C, or B and C, right? Like that. And the first thing we can do is we can use De Morgan's on this. So just like we were showing above, we can use De Morgan's on this, so we get not A, or, and then not the other thing, right? So this is not B, not C, or BC. Okay? And now we can use De Morgan's again. Okay? So this is kind of gross, but if you just keep using De Morgan's, you'll eventually get the answer. So this stays the same, but we use De Morgan's on the right side of the or sign, and we get that this is equal to not B and not C, right? And the whole thing is ANDed with not BC, right? So this is 2 nots, okay? And then we can use De Morgan's again, right? So this whole thing becomes B or C and not B or not C, like that, okay? And now that we're here, we can sort of FOIL it out again, right? We get not A, or B and not B, or C and not B, or B and not C, or C and not C. We know that these two go to 0, right? So these two go to 0, and so we're left with not A, or C and not B, or B and not C. Now we could try using the uniting theorem, but it's a little bit off, and you can't actually do anything with the uniting theorem. So this is our final answer. Okay, cool. So now we know how to repeatedly use De Morgan's law. Okay. So our final question is 1.1d for the section, and 1.1d gives you this really, really long expression. It looks like this: not A and A or B or A and A or not B, like that. Okay. And what we notice here is that we can distribute. That's the first thing I'll do. Not A and A, or not A and B. That whole thing is ORed with A, B, or I guess A, or A not B, or B not B, right? Now we know that A times A is, or A and A is just A, right? So this whole thing is A. So let's just rewrite it as A. And so is this, right? This whole thing is A, not B. And we know that not A and A is actually 0, right? So this goes away. So what we're left with here is not A and B, right? Or A and B, right? Or A and not B, right? Or B and not B. And B and not B, once again, is 0, right? So that's gone. Okay. So now you'll notice, now we can once again factor out an A, right? That's what we were doing before, and we can just do it again. So we have not A and B, or A and 1 or B or not B, right? And we know this whole thing in here goes to 1, right? Because it's all ors. So this all goes away, and what we're left with is not A and B or A. And once again, our friend the uniting theorem comes in, and we get A or B as our final answer. Okay. Okay, let's talk about logic gates. So, being good 621C students who have completed midterm, project 3 now. We should know all these already, but I'll just go over them anyway. So the first gate is not, right, which looks like this. And basically it takes in as input A and outputs not A over there on the right. Okay. The next gate we have is OR, okay, or sorry, AND. I'll do AND. AND looks like this. Okay, it has two inputs, A and B, and over here we get A and B, like that. Okay. The next gate is OR. And OR has two inputs, A and B, and the output is A or B, right? No surprise there. And then finally we have XOR, right? XOR looks like OR, but with two of these things on the left. I don't know what they're called. And the difference between AND and OR, right, is that AND has this straight edge on the back, and OR it's curved. That's the difference. Okay. The last three gates are sort of the NOT variants of AND, OR, and XOR, right? If you stick a NOT gate in front of an AND gate, you get a NAND gate, right? And that looks like this. So we have A and B. They go into the NAND gate like this. And what comes out is A NAND B, like that. Okay. The NOR gate, it's basically the same idea, right? So let's make this more obviously a NOR gate. Okay, so that's A NOR B. And finally, the XNOR gate looks like this, right? It looks like an XOR gate, and then it has this NOT at the end, right? So they probably NSHOR didn't quite slip off the tongue, so we got XNOR instead. Should probably be thankful for that moderately. Okay. 2.2a asks us to write out a NAND signal or a NAND gate in terms of AND and OR. So you'll notice what a NAND gate is it's basically just not AND, right? And so the answer is just this, right? Not A and B. But what if we got some sort of gate that wasn't obviously NAND or NOR, and we couldn't just write out the expression for it like this so easily? So I'm going to tell you how to do this using a sum of products. So the first thing we do is write out the truth table for NAND. Okay, so here's A, B, and A NAND B. Okay. So I'm going to write out every single combination of ones and zeros, of which there are 4. And we'll notice that A NAND B is 1 in all cases where one of the two outputs is 0, and it's 0 in this case, right? So to come up with a Boolean expression from the truth table, we just find all the rows where the expression is 1, right, which is these 3 rows, right? By expression, I mean this column, okay? So I find all the rows where the column where the expression is 1, and I sum them up, okay? So this is called a sum of products, once again, sum of products. Okay, so I get A and not B, or not A and B, or not A and not B, right? So that's why it's called a sum of products, is because you have some products, which are ands, and you have some sums of them, which are ors. So it's a very fitting name. Now we can just do the same thing for XOR. So for XOR, we have A, B, and A XOR B. Right, and for XOR, we know that if they're different, then it's true, right? Otherwise, if they're the same, it's false. So once again, we can write our sum of products, and this is, we know that only this row and this row are 1 in the A XOR B column. So these are the only 2 rows we care about, and so our sum of products for XOR is that A XOR B is equal to A and not B, right, which is this row over here. And then the other option is not A and B, which is this over here. Okay. So this expression A and not B, or not A and B, is equal to A XOR B. Okay. Now finally we have our XNOR, which says it's like not XOR, right? I mean, there's plenty of ways you can do this. You could even do not of this expression up here and then just simplify it using the Boolean logic expression, the Boolean logic properties from part 1. But we'll just write out the truth table for it. So we know that the truth table for this is just the complete opposite of XOR. So it's only one if they're the same. And so we can use sum of products to get that A and B, or not A and not B, have to be true for A XNOR B to be true. Okay. Now the last part of this question asks you to create a AND gate using only NAND gates. Okay. Now that, I guess it's like a cool party trick that you can pull, like, hey, look at me, I can juggle, I can play the accordion, I can create an AND gate out of only NAND gates, sort of thing. So, yeah, maybe if you learn this trick, you can make some friends or something, I don't know. I think the main trick is that if you take A and NAND it with itself, then you actually get not A, right? And if you're not convinced that, you can draw out a truth table. So, if I want to create an AND gate using only NAND gates, what I want to do is I want to take A NAND B, right? This is the opposite of what I want, and I just want to not this whole thing, right? So my goal is to get not A NAND B. And we know we can get not something by just NANDing it with itself, which is what I said here, right? And we know we can get A NAND B by NANDing A and B, and we have access to NAND gates, right? So to draw this circuit, what I'll do is first I'll do A NAND B, okay? And then I want to do not of this, right? So what we have here is A NAND B, and my goal is to get not A NAND B, because this is equal to A and B, right? So I need to not this, and what I'll do is I'll just put it into a NAND gate with itself, like this. So it's really ugly. And what comes out here is not A and B, which is A and B, okay? Let's talk about state. Okay, so I want to talk about state, which means I'm going to talk about waves, okay? Because this is how we represent electrical signals. Okay, so here's an example of a wave. Okay, and waves have times, so over here is time 0, and over here is time 6.5, over here is time 13, 19.5, and 26, right, etc. So you'll notice that the distances between two corresponding peaks, for example, are the same, right? So this will be the same distance as this. I guess I didn't draw it in, so you shouldn't have noticed that, but it is. Let me define some words. Okay, so the peak, this is when the wave is high. Okay, and there's also a trough, which is when the wave is low. Okay, so this is a peak, and this is a trough. Okay, and we have something called a period. Okay, so this is a period right here. Okay, so what is a period? It's the time from a peak to the next peak. Alternatively, it's the time from a trough to the next trough, but those mean the same thing. Okay. So let me come up with an example. All right, and this is the example from your worksheet at the very top. it shows at the very top of page 3 of your worksheet, it shows you an AND gate and two inputs, and it shows you this chart. Okay, the chart looks like this. You start off low and then go to high, okay, and then go low. High for a bit, low for a long time, high, low, high, and then it just sort of tapers off like that. Now we have to draw the output, okay? And what this question, all right, you should read the question before we go over this. But the question says that you have an AND gate, right? The AND gate looks like this, and has two inputs, A and B, okay, and there's an output. And there's a propagation delay of 2 picoseconds for this AND gate. Okay, so now I've drawn the question out. It says that you have an AND gate like this. There's two inputs, A and B, and I've drawn the waves for those inputs up here. The propagation delay of the AND gate is 2 picoseconds, which means that will take 2 picoseconds for the output to appear after the inputs have appeared. That's the propagation delay. So let's start here. At 0 picoseconds, we don't know what the output is yet because the output takes 2 picoseconds to delay. So we actually have an undefined output for 2 picoseconds. Okay, and this is how we define undefined. Right, so this means we don't know if it's high or low. Okay, now 2 picoseconds after 0, the output is propagated from the input. So the inputs are low and low and low over here at 0. Okay, so that means that at 2 picoseconds, we need low and low because this is an AND gate. So 0 and 0 is 0, right? And we know that this output will be there for a whole 2 picoseconds, from 0 to 2. Okay, so let's go 2 picoseconds here to 4. And now we switch actually, because we look at our inputs. Now our inputs are both high, right? So our inputs are high here and high here. So if our inputs are both high, that means that our output is now high because 1 and 1 is 1. So now we're going to go high until 6. Okay, we're going to go high until 8 because it's high for 4 picoseconds. So we need to go high for 4 picoseconds over here. So now it's 8. Okay, now A and B are both low. Okay, so that means that at 6 plus 2, because of our 2 picosecond delay, which is 8, we will go back down to low, okay, for another 3 picoseconds until 11. And the reason it's 3 is because we're low for 3 picoseconds in both A and B, between 6 and 9. Okay, now at 11, we can go back up to high. And the reason we're going back to high is because A and B went up to high at 9. Okay, and then we're at high for 2 picoseconds. Now we're high until 13. At 13, we go to low for 2 picoseconds because that's how much time it was A and B were low between 11 and 13, right? So you'll see a pattern here that actually this wave just emulates the one in A and the one in B. It's just a little bit delayed, right? So it's just a little bit after the one in A and B, but it's the same wave. Okay. So now we've had this quick example out of the way. Let's go over some more terms. Okay. So the first term is setup time. Setup time is defined as the amount of time an input must be stable before a rising edge. So the clock will have a rising edge, but this input has to be stable for setup time before the clock has a rising edge in order for the input to count. Okay. We also have a hold time. The idea of the hold time is the same as the idea of the setup time. It's the amount of time an input must be stable after a rising edge. So the setup time and hold time are both very important, and they're very similar in what they do. Now finally, we have something called the clock to Q delay. The clock to Q delay is the amount of time after a rising edge until the output updates the input value. And it's important to note that this actually includes the hold time. Okay. So what we've been looking at here is that the propagation delay is 2 picoseconds, so it takes 2 picoseconds to propagate. And now we're going to be looking at a delay from the rising edge of the clock. Let's talk about the example on the discussion sheet at the very bottom of the third page. Okay, so in that example, we have a circuit which includes a register. So here's the register, okay, and into the register there's a clock. So this means that now we have to use the clock to Q delay and the other delays involved with clocks. Okay, we also have an input and an output, right? And you can see this on the discussion, hopefully. Okay. You'll notice that we're given that there's a clock signal. Okay, and actually before we get to that, we're given some time. So let's write those down. Okay, we have a setup time. That's 2.5 picoseconds, and a hold time. That's 1.5 picoseconds. And finally, we have a clock to Q time of 1.5 picoseconds. Okay, and we're also told that the clock period is 13 picoseconds. Okay, so, and we're given a clock. Okay, and the clock looks like this. So here's my clock, and I'll just draw it out next to it. It's low, and then it's high, and it's low, and then it's high. Since we know that the clock is period 13 picoseconds, we know it starts off at 0, right? And we know that this is a trough, right? So from the beginning of a trough to the beginning of the next trough, which is here to here, our period is 13. So that means that this is 13 picoseconds. We know this is 6.5 because we just divided it in half. Same goes over here, right? Okay, cool. So now we're going to also get an input, and the input is also given to us. For some reason, they didn't draw times on these inputs in this discussion, but times should be given because otherwise we won't be able to tell about setup time and hold time. So we're just going to assume that they gave us some times. So, okay, now I'm going to figure out the output. Okay, so the output only updates on the rising edge of the clock. Okay, the rising edge of the clock is what causes updates in our circuit. So the rising edge of the clock is like, for example, here. You see, because the clock is going from a trough to a peak. That's what constitutes a rising edge. And there's also another rising edge here. Okay, this is not a rising edge because this is a falling edge. Okay, so we know that our output will only update on the rising edge. And in fact, we don't know what our output starts off at. That's why it's undefined. So that's why we have this big line here. This is undefined from 0 all the way to 6.5. Okay. Now at 6.5, we actually read what's at the input and propagate it to the output. That's because in our circuit right here, right, all the circuit does is it takes something from the input and sends it to the output. It doesn't do any sort of calculation on it. It just puts in the register for a clock cycle. So our register is going to be, or our output is going to be undefined for 6.5 seconds, but right here at 6.5 seconds, we're going to get our input from the input, and then we're going to propagate it over to the output. But it doesn't happen immediately, right? It happens after the clock to Q time. There's a little delay between when it shows up at the input and when it shows up at the output. So the output isn't going to update until 1.5 picoseconds after the rising edge of the clock, okay? That's because we define the clock to Q delay as the amount of time after a rising edge until the output updates the input value, right? So it follows the definition. Okay, so let's wait another 1.5 picoseconds, undefined, okay, until 8, right? Because this right here is 6.5. So we waited 1.5 more picoseconds and we got to 8. Okay, so now we can update to the input value so long as our setup time and hold time are not violated, right? So remember that our setup time is the amount of time the input must be stable before rising edge. The hold time is the amount of time the input must be stable after a rising edge. So let's check to make sure our setup and hold times are not violated. So we want to make sure our setup time and hold time are not violated. So right here it says our setup time of our circuit is 2.5 picoseconds and the hold time of our circuit is 1.5 picoseconds. We want to make sure that we do not violate those times. So we know that the setup time, right, is defined as the amount of time the input must be stable before a rising edge, and the hold time is the amount of time the input must be stable after a rising edge. So right here we have our rising edge and we have our input, and we want to make sure our input right here is the setup time before the rising edge, and here's the hold time after the rising edge. Okay, so this is a setup time, and this is the hold time. It's the amount of time it's stable before and after. Okay. It's not stable anymore at 9 because it changes, and at 4 it also changes. Okay. So the setup time right here, we notice it's from 4 to 6.5, so it's 2.5 picoseconds. And our hold time, we notice, is from 6.5 to 9, so it's actually also 2.5 picoseconds. Okay. So this circuit has enough time to set up and hold, because as you can see, there's 2.5 picoseconds of stability before the 6.5 time step, and there's 2.5 picoseconds of stability after the 6.5 time step. We just need 1.5 picoseconds of stability after and 2.5 picoseconds before. So this is totally fine. If you're confused about this sort of thing, you can think of an analogy to a camera, right? So at the rising edge of the clock, you are taking a picture. But if somebody like runs in front of the camera beforehand, right, as the shutter closes, then the picture is going to be really blurry, right? So we want to make sure the picture is not blurry. So that's this whole idea of having a little bit of time before and right after taking the photo. And at those times, the input needs to be constant. It can't be unstable. Otherwise, we're not going to get a good reading. So we're not going to know what our output is. Because we got a good reading, because our hold time, right, which is actually 1.5 picoseconds. So all we needed was for this to be stable, or up to 8. Now we have a good picture. And so we can propagate the input to the output. So what was the input here? It's high, right? So the output is now high, all the way until the next clock, rising edge of the clock. Okay. So now, at the next rising edge of the clock, we go back to our input, and we check, are we violating our setup time and our holds time? So our setup time, remember, is 2.5 picoseconds, and we notice here that we have 17 to 19.5, so this is 2.5 picoseconds. So this is fine, okay? And after this, now we have another 2.5 picoseconds. So this is also fine, right? We needed at least 1.5 picoseconds, okay? So what that means is that now we can propagate this value over here, right, which is low, to the output. Do we propagate it now? No, because we have to wait for the clock to Q delay, right? And the clock to Q delay, once again, is 1.5. So we're going to go 1.5 after 19.5. That takes us to 21. And then we go too low, okay? And that is our output. Cool. So now I'm going to do 3.1, which involves doing this analysis on 2 more circuits. Okay. Okay, so I've drawn the clock and the input from your worksheet, and we're given in this problem that the clock period is 8 picoseconds. The clock to Q delay is 2 picoseconds. The setup time is 4 picoseconds, and the hold time is 2 picoseconds. Okay, and that NOT gates have a 2 picosecond propagation delay. Okay, so once again, the worksheet doesn't include numbers for some reason. These questions usually include numbers, but with this one, you can figure out the numbers yourself. So just start off at 0. I could have started at 0 here as well, but since nothing really happens back there, it doesn't matter. As long as everything relatively is good, it doesn't matter if it's absolutely some number, because you could start at any time, right? So this would be -4 then, time step-wise, and it would still work out. But whatever, okay, it's arbitrary. What is important is that your periods are 8 picoseconds, right? So here's my peak-to-peak period is 8 picoseconds, and that's why I got these numbers, right? And now if I look at the circuit, you can tell that this input sort of just goes until 10 picoseconds. This is 10. It doesn't tell you, but I guess you can just guess on this one. This one is 14. This is 20. And this is 36, right? Because it lines up. I think on an exam, we would give you the numbers. Okay. So now here's S0, right? And we need to draw S0. What is S0? Well, S0 is the output of this register, right? S0 is the... Oh, no, I erased too much. Okay, S0 is the output of that register from the input after the clock to Q delay. Okay, so let's start off by drawing the rising edges of the clock, because that's what we care about. That's when stuff updates, right? Stuff doesn't update until the rising edge of the clock. So the rising edge of the clock is here, 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 here. Oh, that's not right. Here, here, and here, right? Because those are the rising edges. Okay. So now S0, right? S0 starts off undefined. Once again, I mean, look at that. It's just undefined. And then here, at the first rising edge, it's able to update, okay? So what does it update to? It updates to low. And it updates to low given that we passed the setup time and hold time requirements, right? Now, as you can see, we definitely passed those, right? The setup time is 4 picoseconds, and the hold time is 2, and we're definitely in the clear here beforehand. We have a whole 4 seconds there, 4 picoseconds, and our hold time, 2 picoseconds, we're in the clear here as well. As you can see, it's stable for that time. So we're going to switch to low right after the clock to Q delay, which is 2 picoseconds. So you got to be careful and remember the clock to Q delay. So at 2 picoseconds, we switch to low, okay? And now I'm just going to start going 2 picoseconds after each rising edge of the clock because we've realized that we're not going to switch until the clock to Q delay anyway. So I'll just draw it up until 10, okay? So now what happens at 10? At 10, we have to make sure that we passed our setup time and hold time, right? So our setup time is 4 picoseconds, and that's fine, right? It's stable for those 4 picoseconds. Our hold time is 2 picoseconds, and that's also stable, right? I mean, I drew a really, like, it's not really to scale, but it's definitely stable from 8 to 10, right? So that means that we can continue being low, okay? Because it's low here, so we're just going to continue what it is in the input. So now we're just going to go until 12. I mean, not to 12, until 18. Okay, so at 18, now we have once again have the opportunity to become low again, right? Which is great, whatever. But we want to make sure that we pass our setup time and hold time, right? So we look for our setup time, which is 4 picoseconds. We notice that now, for the first time in this worksheet, we've violated our setup time constraint. And so we have to go to undefined because we didn't get an accurate reading. It needed to be stable. The input needed to be stable for this entire 4 picoseconds to get an accurate reading, right? But it wasn't. So we were unable to take the photo, basically. It was a really blurry photo. And so how we represent a blurry photo is, once again, we go undefined until 26. Okay. Now at 26, we have the opportunity to go to high, so long as we have satisfied our setup time and hold time. And as you can see, we've satisfied it 4 and 2, right? Totally satisfied. And so we will go to high. Why do we go to high? Because that's what the input is. Okay. Now 34, right? At 34, we have the opportunity to stay at high. And I guess spoiler alert, we do manage to stay at high. So we will go all the way to 40, 42, and at 42 we will go to low. Okay. Cool. Now we get to do S1 and out, okay? Now, S1 is the result of S0 put into another register and subject to the same thing, right? So S1 is undefined up until 2, right? Because that's the rising edge of the clock and the clock to Q delay. And after the clock to Q delay, now we get to propagate the undefined back down, right? So, I mean, whatever, right? We either, like, we can check to see if we violated the setup time and the hold time, but it doesn't really matter because either way it's going to be undefined. So we can just continue the undefined until 10, okay? Now, at 10, we check to make sure that we have the setup time and hold time, and look at this, it's like flat forever. So yes, we have not violated the setup time and hold time. So we get to be low, which was what S0 was here, right? Until 18. And at 18, we get to continue being low because that's what S0 was here, right? And we have now violated the setup time or hold time. And now we're at 26. And at 26, we get to be undefined again because that's what S0 was here, right? We just get to propagate down what S0 was. Okay? Up until 34. And at 34, we get to go high again. Okay? And once again, here at 42, we also get to go high again. But we're already high. Okay. Now for the last part, we get to do the output. The output, we get to propagate down this undefined, right? So we start off undefined up until 2. At 2, we get to propagate down the undefined from S1 over here. So we continue being undefined until 10. At 10, we get to propagate down the undefined once again from S1. So we get to be undefined until 18. At 18, we get to propagate down the low. At 26, we get to propagate the low again. At 34, we get to propagate the undefined. And then at 42, we go high. Okay? So that's our circuit. Cool. Okay, so once again, I've drawn the next circuit. In this circuit, we have the input A, right, which goes into the register. And then on the rising edge of the clock, it's propagated out as R1. Okay, and then on the rising edge of the negative clock, right? So here's the not clock. It gets propagated out as R2. Okay, so there's a little bit of combinational logic involved. And as you can see, we've given you the clock. So here's the clock. It goes from 0 to 48. And then here's the not clock, which goes from 0 to 48 as well. And as you've noticed, probably, the not clock is not actually the not clock. It's the not clock shifted by 2. And the reason it's shifted by 2 is because there's a propagation delay of not gates right here, right? 2 picosecond propagation delay. So the not clock would actually be high, low, high, low, high, low. But because the not clock takes 2 picoseconds, we have to shift this whole thing to the right by 2 picoseconds. And we end up with this, right? We end up with this not clock over here. Okay, let's do some analysis on this circuit. So we'll start off with R1. Right? Now, R1 starts off undefined, right? Like they always do. And actually, first we should draw the rising edges. So here's the clock rising edges. Let's do R1. R1 will start off undefined until 2 picoseconds after the rising edge of the clock because of the clock to Q delay. At that point, right, we're going to go and look at our input A, and A does not violate the setup time or the hold time restraints because there's 4 picoseconds here and there's 2 picoseconds here. So we're going to go and we're going to propagate high. Okay. Now high has been propagated all the way until 14, and we notice once again that the restraints are not unsatisfied, so we are going to propagate low from A down here, and now we're going to propagate high from A, right? Once again, we propagate high from A. Now we propagate low from A, okay? And once again, we propagate low from A. So that's what our final waveform looks like. Okay. Now we get R2, okay? R2 is the same thing, but on the not clock. So now we get to go on the rising edge of the not clock shifted by 2 picoseconds, right? So let's get rid of these rising edges, and let's draw the rising edges that matter for R2. And those are these, right? Oh my. Oh my. Okay. So let's propagate from R1, right? Remember, the thing that gets propagated to R2 is the thing that goes into the register. So R1 is the thing going into the register. So we should look at R1, okay? I always see people looking at A, but A is all the way over here. It's not being propagated to R2. That's R1 is being propagated to R2. Okay. So R2 will start off undefined, like everything does, until 6. At 6, it will propagate what was in R1, which, I'm sorry, not at 6, right? Ha, good catch, guys. Because the rising edge of the clock is now at 2. So now we go 2 past the rising edge of the clock to 4, right? So now 4 is where we're going to change R2. Now R2 doesn't change because R1 is undefined at 2. So now we get to go undefined until 12, okay? And at 12, now we get to change to high, okay? Because that's what R1 was at 10. And now at 20, we're going to change to low because that's what R1 was at 18. Okay. At 28, we get to go high. At 36, we get to stay high. And at 44, we get to go low. Is that the answer? Cool, I did it right. Nice. Okay. In 3.2, we are told that register A and register B have set up hold and clock to Q times of 4 nanoseconds. So we've gone from picoseconds to nanoseconds for some reason. Not that it really matters. Okay, our hold time is also 4 nanoseconds, and our clock to Q time is also 4 nanoseconds. We're told that all logic gates have a propagation delay of 5 nanoseconds. Okay, and we're also told that register C, okay, so these are for register A and B. Okay, we're told that register C has a setup time of 6 nanoseconds. Okay, and now we're asked, what is the maximum allowable hold time for register C, and what is the minimum acceptable clock cycle time for this circuit, and what clock frequency does it correspond to? Okay. So some formulas that might be helpful are that the maximum hold time for a register is the clock to queue time plus the shortest combinational logic time. Now, what does this mean? It means that if there's more than one path through a circuit, we're going to find the one that costs the least amount of time. So, for example, if we could go from register A to register C like this, or like this, or like this, we have to go and find the shortest of those three paths in order to find our shortest combinational logic time. Okay. We also have a formula for the minimum clock cycle time. And the minimum clock cycle time is the clock to queue time plus the longest combinational logic time plus the setup time. Okay. So what does that mean? Instead of finding the shortest path, we would find the longest path. And now we also have to add the setup time as well. Okay. So this whole thing sort of makes sense. For a clock cycle to happen, you need to be able to satisfy the hold and setup time, right? If the clock cycle is too short for a hold and setup to occur, then of course everything will be invalid. We said above, the hold time is actually included in the clock to queue time, so that's why we don't count it twice. Okay, and the longest combinational logic time is the longest amount of delay we need, so we need to clock to that, right? That's our critical path of the circuit, which is why this is also known as the critical path. Because this is our minimum clock cycle time, this is the fastest we can clock our circuit. So our fastest clock, which is a frequency, is just 1 over our minimum clock cycle time, or our critical path, right? So with this knowledge in hand, now we can solve this problem. The maximum allowable hold time is just the clock to queue time plus the shortest combinational logic time. Okay, so the clock to queue time of register A, because that's what we're leaving, that's what we're propagating out of, right? Or register B. We know that both of them have a clock to queue time of 4 nanoseconds, so our hold time, our max hold time, I should say, is 4 nanoseconds plus the shortest combinational logic time. So what's the shortest combinational logic from register A or B to C? We know that all the logic gates take 5 nanoseconds. So this path right here takes 15 nanoseconds because it goes through 3 gates. Okay. What about this path? That one also goes through 3 gates, right? But if you look closely enough, you'll always find one that's kind of shorter than the rest probably. And that's this one, right? Which only takes 10 nanoseconds. So our max hold time is 4 nanoseconds plus 10 nanoseconds for this path, okay? And that's actually about it, right? So our max hold time is 14. Now, what about our critical path, or our min clock cycle time? So our min clock cycle time is the clock to queue time once again, right? So it's 4 nanoseconds plus the longest combinational logic time plus the setup time. So what's the longest combinational logic time? It's 15, right? It's the other ones we found. So something like this. There's plenty of them, right? You could also do the other one I found. So that's 15 nanoseconds, and we're also going to have to add a setup time, and we know that register C's setup time, right, is 6 nanoseconds. Notice we use register C setup time because we're entering register C. So we use 4 nanoseconds when we're exiting register A or B, right, because that's register A or B. Setup is for register A or B. The hold time is for the setup time is for register C, right? The clock to queue or hold time is for register A or B because that's what we're leaving, right? We need to set up register C, but we need a hold from register A or B. Okay, and now this whole thing is just equal to 25 nanoseconds, which means that our fastest clock is just 1 over 25 nanoseconds, which is 40 megahertz around if you do the math. Cool. Well, that was it. Yeah, See ya.